One term we will use a lot in thermochemistry is enthalpy. Enthalpy is the total internal energy a substance has. It is represented by the letter H. Keep in mind that enthalpy is a state function. This means that it only depends on the initial and final state and not on the path that is taken to reach that state. I'm telling you right now, this is something chemistry teachers love to ask. It's a question that shows up on the AP exam as well. What do we mean by enthalpy state function? So make sure you understand that. The opposite of a state function is a path function. So you have talked about these kind of functions. For example, distance is a path function, but displacement only depends on the initial and final positions. So that in chemistry terms would be a state function. The equation that is used to calculate enthalpy is H equals U plus PV, where U is the internal energy of the system. The internal energy of a system is usually measured in terms of its translational, rotational and vibrational energy. Translation means that molecule A or atom A is at one spot and then actually physically moves to another spot. Rotation is when something is moving along an axis, clockwise, counterclockwise. And vibration happens when a molecule vibrates either left, right, or something could vibrate. Now, the thing is, right now we are not so concerned about calculating the absolute enthalpy values. What we are more interested in is being able to determine the change in enthalpy of a reaction. So going from reactants to products, what is the difference in enthalpy, which we call delta H. So this is defined as the total of the enthalpy of the products minus the enthalpy of the reactant. This is an important equation. You should keep this in mind, but it shouldn't be very hard because it is talking about final minus initial, which is what change in most entities like change in temperature, change in pressure is also measured as. Okay, and this enthalpy is the heat of reaction. It corresponds to the amount of heat absorbed or given off during a reaction. We just talked about this. So we said if the bond making releases more energy, then there is net heat produced from a reaction. And if the bond making releases less energy than what was acquired by the breaking of the bonds, the net energy is absorbed by a system. This can be shown in a potential energy diagram. So let's look at this example. You start at reactants which are at some lower energy, and then you end up with products which are at some higher energy. So this means this amount of heat is or enthalpy is added. So such a system is called an endothermic reaction. Here the enthalpy of the products is above the enthalpy of the reactants. Therefore, delta H term is positive because this term is larger and then you're subtracting a smaller term from it. Another way to write this would be reactants plus heat forms product. Okay. Similarly, there could be the opposite situation where the reactants have more energy than the products, and that would be shown like this. So you start at some reactant value, and then as you get down to the products, you are actually losing energy to the surroundings. Because the products have lower energy than the reactants, this number is higher and this number is lower. So then delta H would actually be negative. And another way of writing this would be reactants forming products and giving off to the environment. And this kind of a system is exothermic. Another way of thinking of this is exo is exit. So heat is exiting this system, energy is going away. And endo makes you think of, hopefully, enter. Heat or energy is entering the system. A type of question that might show up on a test could look like this. Make a fully labeled diagram for this reaction and they have given you the delta H value. So because this delta H is negative, this tells you that energy is released. This is an exothermic reaction. So all you do is you make your X and Y axes. On this side you write enthalpy. This side says reaction progress or reaction coordinates. And now you want to start with, doesn't matter where you start your reactants, and these are your products. And because energy is exiting or being released, I know that wherever my reactants are, the products must be below the reactants. So let me write the reactants from here. Simply copy from the equation. Let me get the products. I'm sorry, I did never check that this equation is not balanced. Give me a second. Let's balance this equation. Now, if you show your reactants, you show your products, and then you can, if you want to show this arrow going down, you can do that. Or you could just simply write on the side delta H equals negative 890 kilojoule, because that is what was given to you. That's it. So that's a question on your quiz. That's going to be a question on your test. I don't know if that's a question on your exam. I can't predict that just now. But those are easy 2 marks. Make sure you don't lose those 2 marks. Having seen how to draw graphs, let's take a look at 2 other ways in which we can represent this enthalpy change associated with a reaction. So method A shows this delta H value to the right of the equation, just like it was written for you up here in this question. So you write an equation and then you write its delta H value. Now again, look at this. Because no sign is written here, there is an implicit positive sign, and if something is positive, it means energy is entering this system. So this is an endothermic reaction. And when the sign is negative, this means energy is exiting this system. So this is an exothermic reaction. The second way of denoting this heat change is you write heat as a quantity, either as a product or reactant. So here energy is on the reactant side. This means energy is entering the system. So it is an endothermic reaction. And here the energy term is written on the product side. So it means energy is exiting this system. So this is an exothermic reaction. So a question on a test could be, you could be given an equation, and later we will learn how to calculate delta H values also, but you could be asked to write this information in 3 different ways. So we've learned, so what are the 3 ways? Well, one is this method A, method B, and the third one is the graph that we just learned above here. Let's define the term molar enthalpy. Molar enthalpy is the enthalpy change when 1 mole of a substance is undergoing a change. Okay, this is represented by the system delta H and X, where X could be a letter or a combination of letters that indicates the type of change that is occurring. In general, we say that delta H of that reaction is equal to the number of moles involved in that reaction times whatever is the molar enthalpy for that particular reaction. So if you had 3 moles undergoing a particular change, then the total, the net energy change for that reaction would be 3 times whatever is the energy change of 1 mole. I hope that is intuitive and it makes sense. We'll be using this equation many times. Let us look at specific types of molar enthalpies. So we just said that you write an X, a letter or a combination of letters to indicate the type. So here delta HSOL is the enthalpy of solution. So for example, say sodium chloride solid dissolved in water liquid, it would form sodium ions aqueous plus chloride ions aqueous. So this is enthalpy of solution, and if 1 mole of sodium chloride was involved in this change, this would be the molar enthalpy of solution. Similarly, the COM is the enthalpy of combustion. Another way to write this enthalpy of combustion is sometimes we just write delta HC. Combustion is the reaction of something burning in oxygen, and the products are always carbon dioxide and water. You should balance the equation of 2, 2. This is the enthalpy of neutralization. Neutralization is the reaction of an acid and a base. This is the enthalpy of vaporization, going from a liquid to gas. Fr is the enthalpy of freezing, going from a liquid to solid. And delta HR could be the enthalpy of whatever that reaction is. So a question on a test could be, you're given an equation and you are asked to identify what kind of enthalpy this is. Or the other way, you could be given the name of an enthalpy delta H vaporization and asked to give an example of the kind of chemical change that could be represented by this type of enthalpy.
Sometimes you might see this degree symbol on top of an enthalpy. This applies to all of the ones that we have, types that we have talked about just now. This symbol basically represents standard enthalpy. And by that we mean that any reaction where both the reactants and the products are at standard conditions. This is read as delta H naught. An example could be delta H naught combustion. Chemists define standard conditions as 25 degrees Celsius temperature, which is the standard temperature, and the standard pressure is defined as 1 atmosphere. The state of a substance as it naturally occurs at 25 degrees Celsius and 1 atmosphere is called its standard state. So for example, what is the standard state of water? Well, we know that at room temperature and 1 atmospheric pressure, water is a liquid. Another example of a standard enthalpy could be the standard enthalpy of formation. It is written as delta H naught F, and it is defined as the heat change that happens when 1 mole of a substance is formed from its elements in their standard states. So it's important to note that the conditions are that 1 mole of the product must be formed, and this product must be formed from the elements. So that's the second condition. And the third condition is that those elements must be in their standard states. So at 25 degrees Celsius and 1 atmospheric pressure. The enthalpy of formation for elements itself in their standard state is defined as 0. This will make sense if you think of, by definition, so 1 mole of a product has to be formed. So let's say hydrogen has to be formed, 1 mole, and it must be formed from its elements. So what is the element? Well, only hydrogen, and hydrogen must be in its standard state. It's a diatomic molecule, so you just get H2 as a gas. So you see that there really is no change. This is why the delta H formation for an element is always 0. Let us look at an example. So if someone tells you that the delta H naught formation for water is negative 68.3 kilocals, then what this means is that when 1 mole of water is formed from its elements, which are hydrogen and oxygen, and both of those elements must be in their standard states. So at room temperature, hydrogen is a diatomic molecule, so they are both diatomic and they are both gases at room temperature. So when all of these conditions are met, then the energy change that is associated with this reaction is the delta H formation, and the equation is telling us that in this case 68.3 kilocals energy is released. A question on a test could be a multiple choice question when a series of equations are given to you and you're asked whether or not this could be the standard enthalpy of formation. So you're looking for these 3 conditions to be met. So must be 1 mole of product, must be formed from the elements, and each element must be shown in its standard state. Or you could be asked to write the formation equation for something. So in this case, calcium oxide. So you want to make sure that you write 1 mole of calcium oxide solid is produced. This must be produced from its elements. So the elements are calcium and oxygen, and those elements must be in their standard states. So calcium is a metal. The only liquid metal is mercury. So you know that calcium is a solid at room temperature. And oxygen is one of your 7 Hofbrinkel diatomic elements, and you should know that oxygen is a gas. You would not balance this equation. You would just write a half because you want to only have 1 mole of product being formed, and this energy would be delta H naught formation for calcium oxide. Right now we are not calculating this, but we will look at these kind of problems as well when we take up practice problems. The last thing we will do in this enthalpy video is look at 2 properties of delta H. If a chemical equation is reversed, then the sign of delta H is also reversed. So notice here that hydrogen and oxygen are forming water, and the delta H is given to us for this equation, we see that this is an exothermic reaction. So what we are saying is that if you were to reverse this equation, if you were to actually look at water breaking up to form hydrogen and oxygen, then the sign of delta H would change and this reaction would now become endothermic. You have plus 241.8 kilojoules of heat required to break up water. So this is electrolysis. You actually need an electric current to break up water. A second property of delta H is that the size of delta H varies with the amount of the reaction, which basically means that if you multiply an equation with a number, then delta H is also multiplied with the same number. So for example, here you have the same equation, hydrogen and oxygen forming 1 mole of water, and you have a certain value of delta H. But if you multiplied the whole equation with 2, such that every coefficient got multiplied with 2, then delta H would also get multiplied with 2, and the new value would be negative 483.6 kilojoules. Let us take up an example. When you look at this equation, 6 moles of carbon is reacting with 3 moles of hydrogen to produce benzene. The energy change associated with this is positive 82 kilojoules. What this equation is saying is that 82 kilojoules of heat is used up when 1 mole of benzene is produced. Or this equation is also saying that 82 kilojoules of heat is used up or needed when 6 moles of carbon is used up. It is also saying that 82 kilojoules of heat is used up when 3 moles of hydrogen is used up. Now, we can use the properties of delta H that we have just learned to answer some other kinds of questions about this equation. If we wanted to rewrite this equation to show 1 mole of carbon is being used up, then how would we do that? So we want to reduce this 6 into 1, which means you would take this entire equation and divide it by 6. So you would have 1 mole of carbon left. 3 divided by 6 would give you half H2 and 1/6 mole of benzene would be produced. And in that case, you would also take the delta H value and divide that by 6. So this is done by dividing the equation by 6 and similarly dividing delta H by 6. So what is that? 82 divided by 6 is 13.66 kilojoules. Let's practice one more question. So for example, the question says rewrite this equation for 1 mole of nitrogen. You notice that you have half mole of nitrogen given to you and delta H associated with that is also given. So to convert half into 1, you would multiply everything with 2. So you would get 1 mole of nitrogen. If you multiply this with 2, you get 3 moles of hydrogen forming 2 moles of ammonia. And using the properties of delta H, you would also have to multiply this delta H value by 2, and the new delta H value for this reaction would be negative 90 kilojoules of energy. So maybe you could ask yourself, are any of these two equations the equation of formation? Let me call them equation A and equation B. So A is an equation of formation because 1 mole of the product is being formed and they are being formed from the elements in their standard states. But B is not an equation of formation. So even though this says delta H here, it would not be wrong if someone wrote delta H not F for this. Similarly, you could pause the video and rewrite this equation for 1 mole of hydrogen for practice. So you would notice that you need to multiply equation A with 2/3. That gives you 3 moles of nitrogen plus 1 mole of hydrogen forming 2/3 mole of ammonia. And you do the same thing to delta H. You multiply that with 2/3 and you get negative 30 kilojoules. So this is the amount of energy that is released. That's it for delta H for now.